Ma'am, shall we start, ma'am?
Okay, we'll wait for 1 more minute and then we will start. Is my screen visible?
Yes, ma'am.
Okay, thank you. So, anyone would like to recollect what we did in the last class? So, if you could recollect.
Ma'am, shall I, ma'am?
Yeah, please.
Ma'am, last class we discussed about probability
Okay.
distribution. Then we saw what are the types of distribution, normal distribution, Bernoulli distribution, and other things. Then we studied about confusion matrix, ma'am.
And also we saw what is simple probability,
Yes, ma'am.
joint probability, marginal
Marginal
probability,
probability.
simple or marginal we can say, conditional
Yes, ma'am.
probability. Okay. In today's class, we will continue the same concept in probability and also we will learn some of the other statistics involved in it. So in today's class, we will learn about Bayes rule. So before going into the Bayes rule, we will understand what is frequentist and Bayesian probability. To understand Bayes rule, we need to understand these things. So in mathematics, for example, for everything, there is only one rule. To add a pair of numbers, we have only one set of rules to do. But in probability, it is not like this. There is at least two philosophical approaches. Each has its own strength and weakness, but it has two ways. One is frequentist approach, other one is Bayesian probability approach. So there are two ways of doing things. So frequentist approach is most familiar to everybody because it is widely taught and it is used in everyday's discussion. But in machine learning, we use Bayesian approach. So we will learn what is Bayesian approach in this class. But it is not taught widely. But since we are learning machine learning, we will learn about it. The difference between the frequentist and the Bayesian approach is that it's only mathematics and the logic used behind in building those theories for probabilities. That is a major difference. In frequentist approach, we have large number of measurements. So we have large number of measurements. The value which comes the most frequently is the most probable one. So the most occurring value is commonly used. So is the name we use frequentism. So if you want to find the true value, what we do is that we take the most frequently occurring value, which and influence in it. So that is frequentist approach. In the Bayesian approach, there is nothing called as a single measurement. There is no true value to be found. For example, if you are finding the height of a mountain, in frequentist approach, there is only one perfect height, or there is only one single height. But in Bayesian approach, it is not like that. From which point in the ground you are measuring the height, so there can be multiple heights with different varying probability. In frequentist approach, there is only one accurate value or one single value. Suppose you are taking a pencil. So the pencil height is only one in frequentist approach. If there are multiple values, which means that it is inaccurate or wrong. That is how we usually consider, right? There is only one value for the pencil. But the concept of single rule is meaningless in Bayesian. So there are multiple measurements of this pencil and each has its own probability. That is called as a Bayesian approach. Is it clear? Bayesian approach and frequentist approach? So in Bayesian approach, there is no true value is waiting to be found at the end of the process. There are multiple values with multiple multiple probabilities. So the difference between the frequentist and the Bayesian approach is often subtle. They both have different styles of working. Different styles of working with the data. So usually when we say probability, we talk about flipping of the coins. So if you consider, I want to introduce two types of coins here. One is a fair coin. Another one is a rigged coin. Rigged coin or cheater's coin or unfair coin. So what is a fair coin? We have two outcomes in flipping a coin. One is head, another one is tail. So in a fair coin, the probability of getting the head and probability of getting a tail on flipping a coin is equal. But whereas in a rigged trail, it is not that so. So I can introduce a term called bias. Bias is how much bias you are involving in flipping the coin. So if I say a bias of 0.1, I would say in a rigged coin, it has a bias of 0.1, which means that it has a probability that 10% of the time we will get heads. If I say bias of 0.8, that I would say we would expect heads 80% of the time. 20% of the time only we will. But whereas in the fair coin, it has equal chances for getting a head or tail. When you're flipping a coin, you have equal chance of getting a head or a tail. That is a fair coin. But if it has some bias, so bias of 0.1 of getting head means 10% of the time only you will get head on flipping a coin. The rest of the 90% we will get tail. Bias of 0.8 means 80% of the time we will get head. 20% of the time it is tail. So if it is a bias of 0.5 means we will come up with the head and the tail equally. So it is indistinguishable from the fair coin. So a fair coin has a bias of 0.5, which means that 50% of the time we will get head, 50% of the time we will get tail. So that is the meaning, which is called as bias of 0.5. And bias of 0.5 is for the fair coin. The rest of the things it is based on the bias which we fix for the rigged coin. So let us assume you have two coins. Just one is a fair coin, another one is a rigged coin. So just by seeing the coins, we can't distinguish whether it is a fair coin or a rigged coin. Both the coin appear similar. So we can flip and see so that what is the chance of picking a fair coin or what is the chance of picking a rigged coin. Two coins are placed on the table. You have to pick one coin. So what could be its probability? 50-50%. So it can be one is a fair coin, one is a rigged coin. The chances of picking a fair coin is 50%. The chances of picking a rigged coin is 50%. I can write the chance of picking a fair coin as probability of picking a fair coin the chances of picking a rigged coin, I can write probability of picking a rigged coin. So it is 50% chance. So 50% chance, I can write it as 1/2 probability. Is it clear?
Yes, ma'am.
So now we are going to, in the last class, we saw an example of hitting a arrow. So we have an arrow, we are hitting on the wall. Everywhere it has an equal percentage of hitting the wall. So if we have a center circle, hitting the circle is 1/2. So similar to that. So it can be either this one or this one. So there is 50% chance of picking a fair coin or a rigged coin. Let's be more detailed now. So a coin has, so this can be a fair coin, this can be a rigged coin. So a coin has two sides, head and tail. So for the fair coin has a chance of 50% of being a tail. When you're choosing it, it can be a head or in the fair coin, it can be a tail. So it has 50% chance. In the rigged coin, let's assume that head has a chance of 2/3 and tail has a chance of 1/3. Rigged head, rigged tail has a chance of getting 1/3. It is not as equal as the fair side. So chances of picking a fair coin is 50%. In that, chances of getting a head is 50%. Chances of getting a head in a rigged coin is 2/3. If it is 2/3, then chances of getting a tail is 1 minus 2/3, which is 1/3. So we have everything, we have summarized everything which we need in solving this puzzle. So now let us assume that what is the probability that we have a fair coin given that we saw heads. So the coin is head. So what is the probability that it is being a fair head, fair coin? So there are two coins and you have picked a coin which is head. And now we need to know what is the probability that the picked head coin is a fair coin. So the picked head coin is a fair coin. So out of the two heads, one is a fair head, another one is a rigged head. So rigged head probability is more than the fair head. So out of these two heads, we need to pick a fair head. So what is the probability for it? So can I write like this? The probability of getting a fair coin and getting a head, I can write it as a joint probability. This is the probability of getting a head and a fair coin. So I can write probability of getting a head and a rigged coin as a joint probability of P of H comma R is a joint probability of getting a head and a rigged coin. So what is our question? We need to find whether the given coin is a fair coin provided that they are head already. We have seen the head already. So we need to know what is the probability of it being a fair coin. So that is given by the conditional probability. Head is given. So what is the probability that it is being a fair coin? It is given as head can be written by the joint probability of both its being a head and a fair coin. So fair head, I can write it as a joint probability of its being a head and a fair coin. Rigged coin, I can write it as joint probability of H comma R. Is it clear how I wrote this one? Okay. So the previous class we saw about the joint probability. So the joint probability of P of A comma B is written as P of A by B, A given B into P of B. Or otherwise, we can also write it in this way, P of B given A into P of A. So how can I write the joint probability of head comma fair coin? It can be written as probability of H given fair coin into probability of F. So substituting this in this equation, I can get it as P of H given F given H is equal to P of H bar F into P of F divided by the joint probability of P of head and fair plus joint probability of head and rig. Is it clear so far? Okay. Now we cannot find out the value of this one straightforwardly. So what we need to do is that we have to even express this using this joint probability formula. So we will get probability of H given F into P of S divided by, you are replacing it by this formula. So you will get H given F into P of F plus this is P of H given R into P of R. So what is our P of F? So P of F is probability that we picked a fair coin. What is P of R? P of R is probability that we found a rigged coin. P of H given F is the chance of getting a head from a P of H given R is what is the chance of getting a head from a rigged coin. So what is probability of F given H? Probability of F given H is what is the chance of getting a fair coin when we saw head. So initially we saw this probability of getting a fair coin and probability of getting a rigged coin is 50%. So the probability is 1/2. So P of F is 1/2, P of R is 1/2. And what else we saw? We saw that the probability of getting a fair head is 1/2. Probability of getting a rigged head is 2/3. So if it's a fair coin, the probability of getting a head is 1/2. It's a rigged coin, the probability of getting a head is 2/3. So now we have all the probabilities which we needed. So we can substitute in this equation. So we have P of H given, F given H, that is equal to P of H given F. H given F is 1/2 into P of F is 1/2 divided by 1/2 into 1/2. Probability of H given R is 2/3 into P of R is 1/2. Now we have substituted all the values into it. So when you calculate, we get 1/4. This is 1/4 plus 1/3. So we can take an LCM of 12. For 4 and 3, we can take an LCM of 12. So that will be this. That is equal to 3/7, which is approximately 0.43. So the probability of getting a fair coin from a head is 43%. So 43% we will get a fair coin, which means that rest 57% we are getting a rigged coin. So it is not symmetrical. So there is only 14% difference between one flip. Whether we can getting a fair coin and getting a rigid coin, there is only 14% difference. So let's do the same exercise for tails. So what is the probability of getting a fair coin when we saw a tail first? So for that, we have to get a fair tail coin. Getting a fair tail coin has more probability than getting a rigid coin. If you look at here, so getting a rigid coin is only 1/3%. Here, the chances are 1/2. So getting a fair coin has a more chance than getting a rigid coin. So probability of, we can write all the probabilities. Probability of getting a tail out of a fair coin is 1 minus 1/2. Probability of getting a tail out of a rigid coin 1 minus 2/3 is 1/3. So now let us plug in all our values and we can get it. Probability of f given t is equal to probability of t given f. I'm just in this equation, instead of f, I'm writing t. Instead of it, I'm writing t. So we can substitute, we know all the values now. So probability of t given f is 1/2 into probability of f is 1/2 divided by 1/2 into 1/2. This is 1/3 into 1/2. So you have 1/4, 1/4 plus 1/6. Again, we can take an LCM of 12. So this will be 3/5. That is nothing but 0.6% or 60%. So the probability of getting a fair coin out of a tail is 60%. So that means, so there the probability of getting a fair coin out of head is 43%. But here getting a fair coin from a tail is 60%. The results are not symmetrical. If we get a head, we have only 43% probability. But if we get a tail, we have 60% probability that it belongs to a fair coin. So that is the conclusion which we get from this one. So here, if you look at this equation, so if you look at the bottom, so I will rewrite this again. And I'm writing the denominator again. Probability of H given, joint probability of H and F plus joint probability of H and R. If you look at it, this is the probability of getting head by any means, either whether it is a fair coin or a rigid coin. This is the total probability of getting head. It is all possible ways of getting a head. So in our equation, so instead of this one, I can write it as probability of H. Probability of H means the probability of getting a head by any means. So our Bayes rule is nothing but it's a conditional probability which can be expressed in this way. This is called as Bayes rule. Is it clear?
Yes, ma'am.
Is it clear? Okay. So this is the famous Bayes theorem. Anyone has any questions? Okay. So this is a famous Bayes theorem. So the Bayes theorem says that for a conditional probability can be expressed in using this equation. So we will see more about it. So here probability of F given H is nothing but the probability that we have a fair coin, given that we just flipped and saw a head. So to determine this, we are combining three pieces of information. To determine this one, we are combining three pieces of information in the Bayes rule. One is probability of getting a head out of a fair coin. What is the probability of the fair coin, and what is the probability of getting a head? We are combining these three information. So how to remember this equation? So there is an easy way of remembering this equation. So we can write the joint probability of H, F comma H, that is equal to probability of H comma F. We know how to represent joint probability. Joint probability can be written as a conditional probability multiplied by the simple probability. So here also I can write it like this. So divide both the sides by P of H. So if you divide both the sides by P of H, you will get here P of F given H, that is equal to P of H given A into P of A divided by P of H. This is how you can remember how we get it. So also we can write it, each of them, I can write it in terms of A and B so that it is easier to remember. P of B given A into P of A divided by P of B. So P of A given B is nothing but a posterior probability. I'm explaining each term of the Bayes rule. Now we learned how to arrive at the Bayes rule. So now I'm explaining what each term is called as. So this is called as a prior. This is called as an evidence. So we have P of A. P of A is called as a prior. Prior means initial estimate. So it is an initial estimate of whether or not we have a fair coin. So here we have P of F. So it's an initial estimate before flipping the coin. What is the probability of attaining a fair coin? It is an initial estimate. So probability of B is called as an evidence. So probability of getting a head is a evidence. So what is the evidence? Regardless of the way we get it, what is the evidence that we will get probability of the head? So that it is called as an evidence. Probability of B given A is getting the head out of a fair coin. So what is the likelihood of getting a head out of a fair coin? So probability of B given A is called as a likelihood. The probability which we get after all the calculation is called as the posterior probability. Is it clear? So this prior, any doubts? Okay, this prior, we can choose the prior subjectively by ourselves. If we choose the prior by ourselves, it is called as subjective Bayes. If we choose the prior by means of an algorithm or an automatic way, it is called as automatic Bayes. We can even more write this in a more informative terms. So what is the probability of the hypothesis given the observation is probability of observation given the hypothesis into probability of hypothesis divided by probability of observation. So hypothesis means something which is true. Observation means what we are observing about the system or what we are seeing about the system. what is seen in the system. So this is an informative way of writing the Bayes rule. So what is the probability of hypothesis given that the observation is true? So that one can be represented by these three terms, which is likelihood, prior, and evidence. We can kind of find the posterior probability. Is the Bayes rule clear? So what we saw so far. So first we saw about two different approaches in the probability. One is a frequentist approach and the other one is a Bayesian approach. And we saw how measurements are done in both the approaches. So next we took an example of a fair coin and a rigged coin. And then we derived the calculation for the Bayes rule. And finally we obtained the Bayes rule. So finally we obtained the Bayes rule and we saw what is the terms of those Bayes rules. And we arrived at the informative way of writing the Bayes rule. Is it clear? I'll stop here for a minute. If you have any doubts, we will ask and then we'll go to the next topic.
Ma'am, can you tell me the difference between a subjective Bayes and automatic Bayes, ma'am?
Sure. So there is a term called prior, right? So what is this prior? This prior is the initial estimate. So here in our case, in the example which we took, it is the probability of a fair coin. So before flipping the coin, only when we flip the coin, we will know whether it is head or tail. So before flipping the coin, so we wanted to know what is the probability of the fair coin. So that is the initial estimate. That is a prior to our event. Our event is flipping the coin. Prior to our event, what is the initial estimate of getting a fair coin? So that is a prior. So how are we calculating this prior? So if you are calculating this prior if the user is calculating the prior, it is called a subjective Bayes. If the prior is identified by subjective means, it is called a subjective Bayes. If it is the prior is calculated by an automatic way or using an algorithm, if the prior is calculated, it is called as automatic Bayes. Is it clear?
Thank you. Yes, ma'am.
Any doubts?
I'm Sharmagapriya here.
Yes, ma'am.
Where are we going to apply this, ma'am? Any application example?
So we will use in a lot of our machine learning algorithms, ma'am. That is the reason we are teaching that. In machine learning, we will use Bayes, Bayesian approach in many times because there is no single value for it. So there are only different possible. When we have a lot of possibilities, we have a lot of probabilities attached to it. We have only variable probabilities. There is no single measurement. So in such cases, we will use it now. Any other doubts? So whenever you have you have a conditional probability, it can be expressed in Bayes rule and we can solve that one. For that, Bayes rule is used. Bayesian approach is different from Bayes rule. Okay, if you have no next topic. So we will see some of the topics involved in the basic statistics. So we will see what is an expected value. So suppose we have a probability distribution. We are picking one random variable from it. And again, we are picking another random variable from it. So likewise, we pick a list of values. If these list of values are numbers, then we can calculate the mean of them. So the mean of the random variables is called as an expected value. Suppose if the random variables are 1, 3, 5, and say 7, the mean of these random variables can be given like this, right? So you call this as, suppose if x is the random variable, you can call E of x as the expected value. Expected value is nothing but a mean of the random variables. Next, we will see what is called as a dependence. There is again a probability distribution. So you draw one value from it, one random variable from it. Next time you draw another random variable. Next time you draw another random variable. Each time when you pick, it is independent of what you have picked before or what you will be picking after. So every time you are picking a new random variable. So it is independent of what has been drawn before. If this is the case, it is called as an independent random variable. There is also a term called dependent random variable. This independent random variable is easy to work with because we don't have to manage two random variables. When it is dependent on another random variable. So independent means it is easy to manage. Let me give you one example. Suppose you have a probability distribution for the fur length of animals. First, you need to pick up, for example, we have three animals, dog, goat, lamb.
Ma'am, you're not audible, ma'am. Ma'am?
Am I audible now?
Ma'am, now only you're audible, ma'am.
Okay. So first we have to choose the animal. Second, based on the animal only, you can choose the fur length. So choosing of an animal is not dependent on anything. You can pick any one of these three. But the fur length depends on the animal which you pick. So the animal here is a independent variable and fur length is a dependent variable. So did you understand the difference between those two? So if your choices are independent of what is being picked before, then it is called as an independent variable. If your choices depend on other variable, then you call it as a dependent variable. So another variable we will learn is IID variable. IID variable is independent and identically distributed variable. Independent and identically distributed. So independent, we know now only we saw what is independent. What is identically distributed means selecting from the same distribution. If you are selecting from the same distribution, it is called as identically distributed variable. Now let us see another concept called sampling and replacement. So in machine learning, we often build new data sets. So how are we building a new data set? There is a population. From the population, we will select our data set. Are we completely removing the elements from the population, or else we make a copy of these elements and then you create a new data set? That is a question we are asking. There are two ways of building it. One is completely removing the element from the population and putting it in our new data set. And the second thing is that making a copy of it and then adding it in a new data set. So there are two different ways of making a new data set. Let's take one analogy, one simple example. Suppose there is a library. In the library, there is a book shelf. You take each one of the books from here and pile of books on your desk. So how you can select the books from the library? You can choose a book, place it in the table. You can choose another book, place it in the table. But once you have picked a book, you cannot pick the same book again. There can be multiple copies of this book, but you cannot pick the same book again. Once you pick the book is gone. This is one way. Another way is that you take a book, make a photocopy of that book, place the photocopy and replace the original book in the same place. So this can be another way of selecting a book from the library. So in machine learning, we can build the data set in these two approaches. These two approaches will give two different results, but you can use any of these two approaches. So let's start with the first approach, selection with replacement. So selection with replacement. So each time when you remove an element from the pool, original pool, you make a copy of the selection and then replace the original into the pool. So the original pool never changes. Let's start let's get into a small example and then we do it. These are the elements in the original pool. So first time what you do is that you select an element. And then you place a copy of it. Next time, you select another element. You make this is your original pool. This is a new data set we are making. You take another element and put it in the new pool. You make a copy of it and put it in the pool so that it is not changing. Next time what happens? You are picking the same element which you have taken before. So in this way, you can create a new data set which has the same object more than once. So the implication of selection with replacement is that you are selecting a object and then you are replacing the object in the original pool so that the original pool doesn't get altered. So there are some implications in this method. The first implication is that we can select the same object multiple times. Is that the created data set can be of the same size or a smaller size, or even it can be a bigger size. Suppose if you are selecting E 10 times, this is going to be a bigger set. This new data set is going to be a bigger set than the original pool. So you are selecting only E only once and you are not selecting any number. It can be a smaller size, or you are exactly copying the original pool. Then you will be of the original size. The third implication is that the size of the original pool will not be altered. So if you look at the original pool, every time after the selection, the original pool remains the same. It is not getting altered. So these are the implications of choosing it. And the most important implication is that every time the choice is independent. So this time I'm selecting E, but it doesn't matter if I have selected E before also. So we can choose E independent of the previous choices. Our current choice, we can make our current choice independent of the previous choices. Also, it is not going to influence the future choices. So the selections are independent. So next we can see, so far we have seen two things. One is selection with replacement. The other type of selection is called a selection without replacement. So in selection without replacement, we'll take the same example. So first we have 8 elements. So you choose one element, you choose E. Once you choose an E, next time that element won't be present because you have removed it to the new data set. Next you choose F. Since you have chosen F, it is gone from the original pool. Now, if you want to choose E, it is not possible because it is not there. You have to choose something out of this one. So your choices are not independent. Secondly, you will create a database which is of the same size. You can select all the elements from the original pool to the new data set. So you can create of the same size, or you can create a smaller sized data set. But you can never create a data set which is every time you choose that the element is lost. So you cannot choose more than once. The third implication is that you cannot choose more than once. You can select an object only once. So these are the implications in the selection without replacement. So in creating a new data set, there are two ways of creating a new data set from the population data set. One is selection with replacement, and the other one is selection without replacement. The name itself is very intuitive, so you can get it. With replacement means you are making a copy of it in the original pool and then taking out the element. Without replacement means the element is lost in the original data set and you are creating the new data set. So let's take that, suppose if you have 3 elements, A, B, C. So in selection with replacement, you have to choose 2 objects from it. So you can choose AA, AB, or BB, BC, CC, AC. So there are 6 combinations in it. In selection without replacement, there is only 2 combinations, sorry, 3 combinations. So there are 3 elements. You have to choose 2. So there are 2 methods of creating a database. So in one database, in selection with replacement, you have 6 combinations of selecting 2 elements. In selection without replacement, there is only 3 options. So the number of options of creating the data set is reduced in selection without replacement, or else you can say larger data sets can be created with selection with replacement. Is it clear? Is 2 ways of selection clear to you?
Yes, ma'am.
Okay. Next, we will see what is bootstrapping. So would anyone like to give an example of selection with replacement? We saw library as an example, like taking the book and without returning it is selection without replacement, making a photocopy of the book and then placing the original into the pool. It is called a selection with replacement. Anyone would like to give any example for selection with replacement and selection without replacement? Any current real life examples? Anyone would like to make a try? Okay, suppose we are doing your thesis, you would like to, someone who wants to say? Okay, when you're doing a thesis, you will go to your record room and then collect the number of cases. You take the photocopy of the cases, but you don't alter the original data set. You don't alter the case sheets or the case reports present there. You just make the photocopy of it and then come and do you create your sample and then you do your research. The main databases, the main repository is untouched. So this is selection with replacement. So selection without replacement, any example? Let me tell you another example. Suppose we want to measure the mean height of all the people who are alive in the world right now. So it is practically impossible to measure the whole world who are all alive. It is difficult to measure their height and then find a mean height. So what we do, we take a sample from the population. And this sample is selection without replacement. Without replacement, you create a sample. And this sample you create in a reasonable way such that it acts as a proxy for the whole population. With respect to all the properties we wanted to measure, it is going to act as a proxy. And this sample set is built without replacement. Every time you take a person, you're not going to replace that person. You are taken into the sample, and the sample is going to act as a proxy for the whole world population. And then we will calculate the mean. So when you calculate the mean of this sample, it is going to act like a mean estimate for the whole population. So how do we know that if this mean estimate is good or not for the whole population? We would like to express that in terms of a confidence interval. So we can say 98%, we are certain that the mean population is between 3.1 to 4.5 food. So we will express in this way. So we need to know to express a good estimate in terms of confidence interval. We need to know the lower bound of the mean, upper bound of it, and also we need to express the confidence interval. So one way of expressing, not confidence interval, just confidence. So we need to express the confidence. So one way of expressing the confidence is through the technique called as bootstrapping. So bootstrapping has two steps. The first step is creating a sample set
Ma'am, you're not audible, ma'am.
Am I audible now?
Yes, ma'am.
So the first step is to create a sample set from the original population. And the second step is resampling from the sample set. And the resampling is done by selection with replacement method. And the new sample which you create by resampling is called as bootstrap. So you have an original population, you create a sample set from that one. So every time what you do is that you resample and create a smaller data set from the sample set. And that smaller data set is called as the bootstrap. And how do you choose the new sampling is through selection with replacement. Is it clear? And you calculate the mean for the new samples. So every time you calculate the mean, and that will give the estimate of the original population. So the distributions which you are computing for the bootstrap samples is analyzed to give the confidence. So we were talking about it is one way of establishing the confidence is through making the bootstrap samples. So how are we going to establish it? So we will find the estimate from these new samples, and that will help in calculating the confidence intervals or measures of variability. So is it clear? So bootstrap, you have to remember only two steps. First, you have to create a sample set from the original population. And from the sample set, you are resampling again to create smaller samples, which is called as a bootstrap. And the smaller samples, the number of samples can be even, the n can be even 1,000. The smaller samples which you create from the sample set can be as high as 1,000 or even more. So you create the new samples. For each of these new sample, you calculate the statistics, and that statistics will give, from that statistics, we will plot the histogram and we will do the other analysis and identify the confidence intervals and measures of variability. Is it clear?
Yes, ma'am.
So next we
Ma'am, you're not audible, ma'am.
am I audible now?
Yes, ma'am. Now you're audible, ma'am.
Okay. So we will see what is high dimensional space. Anyone would like to tell what is high dimensional space? Anyone would like to try? Okay. So we often think of objects. So these objects can come from hundreds and thousands of dimensions. So generally, suppose if you have one measurement, one piece of data, suppose one piece of data has one value. So this can be expressed in one dimension or in one axis. Suppose we have three sets of one value, height of three people. This can be expressed in x-axis, or you can say it as a one dimension. Suppose one piece of data has two values. So it can be expressed in two axes, or you can call it as a two-dimensional data. So each point here will have a x value and a y value. So you can call it as a two-dimensional data. Suppose if one piece of data has three values, you can name it in three axes. It has three values. So you can name it in three axes, or otherwise you can call it as a three-dimensional data. So any dimension above three, whether it is 4 dimension or 5D dimension or 20 dimension, it is difficult to draw in a 2D space. It is difficult to represent 4D or 5D in a two-dimensional page. So these, anything above 3-dimensional is called as higher dimensional space. In machine learning, most of the time we will be dealing with higher dimensional spaces. So we will see what it is in the next class. And also we will see some of the relationships used in the machine learning in the upcoming classes. So in sampling and replacement, first what we saw here is that we saw what is an expected value. And we saw what is a dependent variable and independent variable. And we also saw about IID variable. Am I audible now?
Yes, ma'am.
Yes, ma'am.
So in sampling and replacement, there are two types. One is sampling with replacement, and another one is sampling without replacement. So we saw two examples for it. And then we saw what is bootstrapping. And then we saw what is higher dimensional space. Why are we looking at higher dimensional spaces? Because most of the data which we use in machine learning are higher dimensional. So we saw what it is. We will, in the next class, we will deal with some of the statistics concepts, and also we will look at information theory. Any doubts?
No, ma'am.
Oh,
No, ma'am.
thank you for joining.
Ma'am,
Thank you.
when will be the next class?
Yeah.
When will be the next class?
So next class is on Friday.
Friday. Okay.
So as usual on Friday. Yeah.
Okay.
Ma'am,
Yeah. Thank you. Yeah.
ma'am, any textbook or reading material would you will recommend for this one material, ma'am?
You can follow my notes. If anything is needed in between, I will suggest in the class.
Okay, ma'am. Thank you.
Excuse me, ma'am.
Yeah.
Yeah, sir had actually told us to join this class. So he said he'll give us more
Sure.
details regarding this class later. So when can we expect any information? Because there are a couple of doctors who have joined here after going for this lecture that happened last weekend.
Sure.
So we have
Sure.
joined here.
Hello?
I have joined
Hello?
here. So,
Hello,
yeah,
can you
can
just
Yes, ma'am.
wait? We made Srinath the administrator. We will send it to you. Thank you.
okay, ma'am. Thank you.
Right.
Okay. Thank you all.
Thanks, Dr. Pratibha. It was a very
Thanks,
clear,
ma'am.
very nice way to explain. Of course, there are doubts, but that we will be sending to you. We'll
Sure.
be right. Yeah.
If any doubts is there, you can stop me then and there, and we can discuss in the class. Even if you want to discuss it privately, it's okay. You can send me a message or you can share it in the group.
Yeah. Thank you so much.
Okay, then. Thank you.
Thank you, ma'am.
Thank you, ma'am.